This will be our first lecture on Chapter 12 on liquids, solids, and intermolecular forces. A preview of the topics we'll be discussing in Chapter 12 for both of our lectures today. We'll be looking at the properties of liquids and solids. We'll be looking at the intermolecular forces, specifically in liquids, and how, for liquids, that builds surface tension and viscosity. Then we'll be looking at some phase changes, which includes evaporation and condensation, as well as melting, freezing, and sublimation. Then we'll be looking a little bit more into detail of these different intermolecular forces. Then we'll be looking at the different types of crystalline solids and what makes water so significant, and it has to deal with the intermolecular forces present in water. So we see here that when we have drops of water, the water drops happen to be in spherical shape, which is shown here. The reason why this is because of the attractive forces that exist between the water molecules that arrange them to be in what we see as a spherical shape. The reason for this is because a spherical geometry shape will end up having the lowest surface area to volume ratio. So most of the interactions that occur within the molecule happens to be in the interior of the sphere and less so at the surface. So the state of a sample of matter, it could be solid, liquid, or gas state, will depend on the magnitude of the intermolecular forces relative to the amount of thermal energy in the sample. So the molecules and atoms that compose matter are constantly in random motion. And as we increase the temperature, the random motion of these molecules and atoms that compose matter, that random motion will also increase. The energy associated with this motion is called the thermal energy. When we have weaker intermolecular forces relative to the thermal energy, the more likely that the sample will be gas. But when we have strong intermolecular forces relative to the thermal energy, then we have more likelihood that the sample would be either liquid or solid. So we see here at the bottom of this slide, we see that the gas state is shown on the left slide, or on the left picture. In the middle picture, we have liquids. And on the right picture, we have a solid. The molecules or atoms that compose the liquid or the solid are going to be in close contact with each other. The difference between the solids and liquids is in the freedom of movement of the constituent molecules or atoms. So in liquids, what we see here is that even though the atoms or molecules are in close contact with each other, they're still free to move around each other. And because of this, we can have the liquid forming the shape of our container because of this free movement of each atom or molecule. Whereas in solids, the atoms or molecules are all in fixed positions, which doesn't allow the atoms or molecules to slide past each other, and therefore Solids do not fit the shape of their container. Although these atoms and molecules are fixed in their positions, the thermal energy does cause them to vibrate about a fixed point. So as we just mentioned in the last slide, because the molecules in liquid water, for example, because they're free to move around each other, they flow around each other and they end up assuming the shape of their container. So when we pour water, we're pouring it as a stream, for example, and we pour it into an Erlenmeyer flask, the liquid will end up assuming the shape of the Erlenmeyer flask. Whereas here we have ice, so that is a solid of water. Here we see the molecules are in fixed positions, so they do not assume the shape of their container. However, as we mentioned, they do vibrate around those fixed positions. So let's look back briefly at some of the properties of gases that we learned from chapter 11. Gases have low densities in comparison to liquids and solids. That's because of the large amount of space between each gas atom or gas molecule. Gases also have indefinite shape. That is that they'll assume the shape of their container. Gases have indefinite volume, which means that they can easily be compressed. Gases have weak intermolecular forces relative to the thermal energy. For example, we have carbon dioxide gas, CO2, which has weak intermolecular forces relative to its thermal energy. In this chapter, we are studying the behavior of these intermolecular forces and how it affects the compounds or the states that have a strong intermolecular force. Liquids and solids have strong intermolecular forces. Let's look at some of the properties of liquids. Liquids have high densities in comparison to gases. Liquids also have indefinite shape. That means that just like gases, they assume the shape of their container. Liquids have definite volume, which means they cannot easily be compressed. Liquids have moderate intermolecular forces relative to the thermal energy. So it is stronger than the intermolecular forces that are present amongst gases. Therefore, we will be looking at liquids in this chapter. For example, liquid water, H2O, has a significant amount of intermolecular forces relative to its thermal energy. We'll also be studying solids in this chapter. Solids have high densities in comparison to gases. Again, this is also because of not having the large amount of space between the gases or between the different atoms or molecules in solids. Solids also have a definite shape. So that is, they do not assume the shape of their container. Solids also have a definite volume, which means that they are not easily compressed. Solids have strong intermolecular forces relative to thermal energy. For example, sugar. And solids may be crystalline, which is an ordered structure, or amorphous, which is a disordered structure. Table 12.1 looks at some of these properties of the different states of matter. Here we have the gas phase. Here are just some of the properties that we went over in the last few slides. So gases have a low density, they have an indefinite shape, they have an indefinite volume, they have weak intermolecular forces, whereas liquids, the liquid phase, has high density, has an indefinite shape, has a definite volume, and it has moderate intermolecular forces, or moderate strength of intermolecular forces. And solids have high density, definite shape, definite volume, and strong strength of intermolecular forces. So without these intermolecular forces, solids and liquids wouldn't exist. If we didn't have these strong intermolecular forces, or these moderate intermolecular forces between solids and liquids, then all of the matter would just be in gas state. In liquids, we can observe several other manifestations of intermolecular forces, which includes surface tension and viscosity of liquids. Surface tension is the tendency of liquids to minimize their surface area. So the stronger the intermolecular forces of attraction, the stronger that the surface tension will be. If we look at this picture here, we see a paper clip floating on water. A paper clip or a water bug will float on water if it's carefully placed on the surface of the water. The reason for this floating is because it's held up by the surface tension of this outer layer of water. Whereas if we're trying to float a paper clip on gasoline, we wouldn't be able to do it. That's because the intermolecular forces amongst the gasoline molecules are weaker than the intermolecular forces among the water molecules. So gasoline does not have strong enough of a surface tension of its outer layer. Viscosity is the resistance of a liquid to flow. So when we have liquids that are viscous, they will flow more slowly than liquids that are not viscous. So for example, we see a picture of maple syrup being poured onto pancakes. Majority of us have used syrup on pancakes or waffles, and we have seen that the maple syrup flows more slowly than does water. And this is because maple syrup is more viscous than water. Similarly, motor oil is also more viscous than water. Oh, I'm sorry, motor oil is more viscous than gasoline. So the viscosity is greater in substances with greater intermolecular forces. So the more intermolecular forces we have, the more viscous our liquid will be. And this is because molecules cannot move around each other as freely if they're attracted to each other with these strong intermolecular forces. So what happens is that these molecules are not able to flow around each other as freely, which ends up hindering the flow. Long molecules, such as the hydrocarbons in motor oil, tend to form viscous liquids because of the molecular arrangement or molecular entanglement. So large molecules such as hydrocarbons. In organic chemistry, we can draw them this way, where each one of these corners represents a carbon attached to at least one hydrogen or more. Well, if we have many of these hydrocarbons, long chains, they'll undergo molecular entanglement, which makes these hydrocarbons, such as motor oil, viscous. Now let's look at the phase changes between our liquids into its gas component. When we have a liquid phase change, changing into its gas state, that's called evaporation or vaporization. And that's when a substance is converted from its liquid state into its gas state. The rate of this vaporization will increase with the following. When we have increasing surface area, when we have increasing temperature, and when we have decreasing strength of the intermolecular forces. So the liquids that evaporate easily are called volatile, while those that do not vaporize easily are called non-volatile. In lab, when and if we deal with volatile liquids, it is very important that we perform experiments with those volatile liquids under the hood, because they evaporate so easily. Otherwise, we would be breathing in a lot of those volatile liquids if the experiments were performed outside of the hood. Now, because molecules on the surface of a liquid are held less tightly than those in the interior, the most energetic amongst the surface liquid molecules can actually break away into the gas state in the process that's called evaporation. So as we see in this lower left diagram, at a given temperature, a sample of molecules or atoms will have a distribution of kinetic energies. So at this lower temperature, we have this distribution of kinetic energies. So some fraction of molecules will have this lower amount of kinetic energy, and the largest fraction of molecules will have this amount of kinetic energy. And at higher temperatures, the largest fraction of molecules will have this amount of kinetic energy. And only a small fraction of molecules will have enough kinetic energy to be able to escape the liquid. And this is shown by this part of the graph that's shown in purple. So this line here represents the minimum kinetic energy that's needed in order for the molecules to escape the liquid state and form a gas state. So any of the fraction of molecules that are able to have kinetic energy higher than this amount are actually escaping the liquid state into the gas state. what we see is at this higher temperature, the red curve, the fraction of molecules that have enough energy to escape will increase. The purple will be shown as a part of the line beyond the minimum kinetic energy to escape. It'll be right below that line. And we see at the higher temperature that that region will be higher. Now, condensation is a physical change in which a substance is converted from its gas state into the liquid state. So this is the opposite of evaporation. Evaporation was changing from a liquid state to a gas state, and condensation is changing from a gas state to a liquid state. At the point where the rates of condensation and evaporation are becoming equal, we call that dynamic equilibrium. And at dynamic equilibrium, once that is reached, the number of gas-water molecules above the liquid will remain constant. So if we look at this diagram here we see we just have liquid initially, but now evaporation is just beginning to occur. So our phase change is going only from our liquid to our gas. Some amount. In figure B, we see that the evaporation is continuing, which we see from these up arrows going from the surface of our liquid into the gas state. But we also see these down arrows, which means that some of these gas state molecules are converting back into liquid state molecule. So that is that we have evaporation still occurring, but now condensation is also beginning to occur. However, we have not yet reached dynamic equilibrium. Once we reach dynamic equilibrium, that means that the rate of evaporation is going to be equal to the rate of condensation. That is, just as many molecules that are changing from a liquid state to a gas state, or that are evaporating, the rate of that is the same as the rate of the molecules that are in gas state forming a liquid state. The vapor pressure of a liquid is the partial pressure of its vapor when it's in dynamic equilibrium with this liquid. Vapor pressure will increase with the following. Vapor pressure will increase with increasing temperature. Vapor pressure will also increase as we have decreasing strength of intermolecular forces. The vapor pressure is independent of the surface area, and this is because just as much because an increase in the surface area equilibrium will affect the rate of evaporation just as much as it'll affect the rate of condensation. Another phase change is boiling. Here we see a picture of water, liquid water, beginning to boil. And in this boiling process, the thermal energy is enough to cause the water molecules in the interior of the liquid to become gas or gaseous water molecules. And this forms these little bubbles in the interior of the liquid. And these bubbles, here we see a magnified view, actually contain gaseous bubbles of gaseous water molecules. Now in this chapter, we'll be looking a lot at heating curves. That is where we have, as we see on the bottom right of our slide, we have the y-axis representing our temperature and the x-axis representing the heat added. So we see here that once the boiling point of a liquid is reached, so for example, we know the boiling point of water is 100 degrees Celsius. Once the boiling point of a liquid is reached, then supplying additional heat will only cause the liquid to boil more rapidly. So that is, the liquid will start changing into gas more rapidly. But it will not change the temperature of the liquid above its boiling point. What we see is that here is our boiling point. At this point, between 20 degrees and 100 degrees, our water is in liquid state, and we're increasing temperature as we add more heat, but we're still in the liquid phase. Once we reach 100 degrees Celsius, then during this phase, the liquid phase is slowly converting into gas state. But notice as we're adding more and more heat, our temperature is staying the same. So as we're adding more and more heat, what happens is the temperature stays the same, but the boiling becomes more rapid. And then finally, once all of our liquid has formed gas, which is right at this point, then any more heat that's added will then start to increase the temperature of the gas. So we see a mixture of boiling water and steam is a gas phase of water, will always have a temperature of 100 degrees Celsius, assuming we have 1 atmosphere pressure. And during the boiling, temperature will remain at 100 degrees Celsius until all the liquid is evaporated. This is very important. The stronger the intermolecular forces are, the higher the boiling point temperature will be. Now the process of evaporation is endothermic. And recall that when we say that a process is endothermic, it means that it's absorbing heat. So when a liquid is converted into its gas state, which is what we call by evaporation, it's absorbing the heat because energy is required to break the molecules away from the rest of the liquid. So our bodies use that endothermic nature of evaporation for cooling. When we are overheated, we sweat, and this causes our skin to be covered with liquid water. As this liquid water is evaporating from our skin, it's now absorbing heat from our bodies, which cools us down. When we have high humidity, that slows down the evaporation process, which prevents cooling. When the air already contains high amounts of water vapor, sweat doesn't evaporate as easily, which makes our cooling system less efficient. Condensation is the opposite of evaporation. So condensation is when we have a gas forming a liquid. And that process is exothermic, which means that heat is released when a gas condenses to a liquid. Now the heat of vaporization is noted by this delta enthalpy of vaporization. And that's the amount of heat that's required to vaporize exactly 1 mole of a liquid. So the heat of vaporization of water at its normal boiling point, and water's normal boiling point is 100 degrees Celsius. The heat of vaporization at this boiling point is 40.7 kilojoules per mole. So that means that in this process of vaporization, we have the liquid state of water forming the gas state of water. Note that the enthalpy of vaporization, or the heat of vaporization, is a positive value, shown here, because vaporization is endothermic, which means that energy must be added to the water to vaporize it. Now the same amount of heat, the 40.7 kilojoules per mole, is involved when we have 1 mole of gas condensing. But when we have condensation, now the heat is going to be emitted rather than being absorbed. So when we have condensation, we have the gas state of water, for example, forming the liquid state of water. And we see here that the heat, the amount of heat here is going to be the same value, but now a negative 40.7 kilojoules. So here, delta H, vaporization, is negative because condensation is exothermic, which means that heat is given off as the water condenses. Again, heat of vaporization is the amount of heat that's required to vaporize 1 mole of liquid. Table 12.2 shows you the heats of vaporization of several liquids at their boiling points, as well as at 25 degrees Celsius. So for water, shown by the chemical formula H2O, its normal boiling point is 100 degrees Celsius. The heat of vaporization at the boiling point, which is 100 degrees Celsius, the heat of vaporization there will be 40.7 kilojoules per mole. At temperatures beside the boiling point, they also have a heat of vaporization, each of these liquids. So at 25 degrees Celsius, the heat of vaporization is 44.0 kilojoules per mole for water. We can use the heat of vaporization of a liquid to calculate the amount of heat energy that's required to vaporize a given amount of that liquid. We'll use the heat of vaporization as a conversion factor between the moles of liquid and the amount of heat that's required to vaporize it. So let's look at example 12.1 from our textbook. Here we'll be looking at using the heat of vaporization and calculations. So here we want to calculate the amount of water in grams that can be vaporized at its boiling point when we have 155 kilojoules of heat. So here we're given the number of kilojoules of heat energy, which is 155 kilojoules of heat, and we're asked to find the mass of water that can be vaporized with the given amount of energy. So we were given 155 kilojoules of energy, and we need to find the mass in grams of water. So here, let's draw the solution map. We're starting off with our kilojoules of energy. Using the heat of vaporization, remember that the heat of vaporization has units of kilojoules per mole. So with that, we can cancel out our kilojoules and convert into moles of water. Then we're close to our answer, but our answer needs to be in grams of water. So to convert from moles to grams, we'll use the molar mass. From table 12.2, we can see that the heat of vaporization at water's boiling point, which is 100 degrees Celsius for water, the heat of vaporization at this boiling point is 40.7 kilojoules per mole. And from the periodic table, we can see that the molar mass of water is 18.02 grams of H2O for every 1 mole of H2O. So to solve this problem, we start off with our 155 kilojoules, multiply that by the heat of vaporization at water's boiling point, which is 40.7 kilojoules per 1 mole of water, and we want kilojoules to be on the bottom and moles to be on top. Now we're dealing with moles of H2O, and to convert moles of H2O to grams of H2O, we multiply that by the molar mass, and the moles of H2O cancel out, and we end up with grams of H2O. So our answer is 68.6 grams. Now, other phase changes are melting and freezing. So as the temperature of a solid is increasing, the thermal energy is causing the molecules and atoms that compose the solid to now vibrate faster. When we get to the melting point, then the atoms and molecules will now have enough thermal energy to overcome the intermolecular forces that hold them at their stationary points. Now the solid can turn into a liquid. So we see when ice melts, water molecules are breaking free from the solid structure, and now they're becoming liquid. So if we look at the heating curve here, we see that below 0 degrees, we are in the solid state. Once we reach 0 degrees, we are now adding more and more heat, which just increases the amount of, or the speed of vaporization. I'm sorry, the speed of melting, which means that we are now going from a solid state, shown here, into a liquid state, shown here. But during this entire process, we now have both solid and liquid still in our beaker, which is shown here. As long as ice and water are both present, the temperature will still be 0 degrees. Once all of that solid has converted into liquid, then as we're adding more and more heat to only our liquid phase, our temperature will start increasing again. So melting is when the kinetic energy increases enough that a solid becomes liquid. Melting is endothermic, Because energy is required to partially overcome the attractions between the molecules in the solid state and free them enough to convert into a liquid state. Freezing is just the opposite of melting. Freezing is when the kinetic energy is decreased enough that a liquid becomes a solid. So melting, we learned, was when a solid is becoming a liquid, and melting is endothermic. Freezing is when a liquid is becoming a solid, and freezing is exothermic. That means that heat is released when a liquid freezes into a solid. So we represent the amount of heat that's required to melt 1 mole of a solid as the heat of fusion, which is shown here. So if we look at water specifically, the heat of fusion for water is 6.02 kilojoules per mole. So as we're melting water, so that is we're going from a solid state of water to a liquid state of water, our delta H, fusion, or our delta H will be positive 6.02 kilojoules. This is our delta H of fusion here, which is positive because melting is endothermic, which means the energy must be added to the ice in order to melt it. If we look at liquid becoming solid, that means that we're having our water now freezing. It'll have the same amount of heat, but now the heat will be emitted, which means that our heat will have a negative sign, or our heat of fusion will be negative. This is because in freezing, we now have an exothermic process, which means that energy is given off as that water is freezing. So again, heat of fusion represents the amount of heat that's required to melt 1 mole of a solid. Table 12.3 gives us the heat of fusion for several substances. For water, for example, it gives us the melting point of water, which is always going to be 0.00 degrees Celsius. And the heat of fusion at that melting point, which is 6.02 kilojoules per mole. We can use this heat of fusion in order to calculate the amount of heat energy that's required to melt a given amount of a solid. So similar to how we had used the heat of vaporization, we can now use the heat of fusion as a conversion factor between the moles of a solid and the amount of heat that's required to melt them. So let's look at an example, example 12.2. Here we want to calculate the amount of ice. So ice is solid H2O in grams that upon melting at 0 degrees Celsius absorbs 237 kilojoules of heat. So here we're given the number of kilojoules of heat energy, and we're asked to find the mass of ice that absorbs a given amount of energy upon melting. We're given 237 kilojoules of energy, and we want to find the mass of H2O in the solid state. This process will be very similar to what we did in example 12.1. Drawing the solution map, we're starting off with our kilojoules of heat. We're using now the heat of fusion to convert between our kilojoules of heat into moles of H2O. And then lastly, to convert into grams of H2O, from moles of H2O, we'll use the molar mass. So we have 237 kilojoules of energy. Multiply that by the inverse of the heat of fusion in this case, because we want our kilojoules to cancel out, so it should be on the bottom, and our moles of H2O to be on top. And then lastly, multiply that by the molar mass in order to cancel out our moles of H2O and end up with grams of H2O. And we end up with 709 grams of H2O. So here we see a heating curve for ice. So in this diagram, it shows a heating curve for ice that begins at negative 25 degrees Celsius and it ends at 125 degrees Celsius. Spend a few seconds correlating sections 1, 2, and 3 with the correct states of water. Right, pause the video if you need more time. Let's do this together. We know at 0 degrees Celsius, we're having a phase change. If we're starting off at a low temperature and increasing in temperature, from negative 25 to 0 degrees, we are in our solid state. And at point 1, we're at 0 degrees Celsius. At 0 degrees Celsius for water, we're converting from a solid into a liquid. So at 0 degrees Celsius, we have both the solid and liquid state. For section 2, we are now starting at 0 degrees Celsius and going all the way up to 100 degrees Celsius. At this point, we are just in our liquid state. And then lastly, once we reach 100 degrees Celsius, for section 3, we are now remaining 100 degrees Celsius. And at this temperature, water starts off with liquid and starts converting into gas state. So at 100 degrees Celsius, we have both the liquid and gas state. And then outside of this problem, if we look at the phases above 100 degrees Celsius, at this section, we would just have the gas state. So here we see the temperature heat energy graph for a pure substance. Again, temperature is your y-axis, and the heat energy in joules is your x-axis. We see at this point, the lower consistent temperature as we're increasing the amount of heat energy, so we're moving to the right of the curve. This is where melting or fusion is occurring. If we were reducing the amount of heat energy, we're actually moving to the left of the curve, and at this point, freezing or solidification is occurring. If we were to look at the second higher temperature at which we have a consistent temperature, this is where if we're increasing the amount of heat energy, this is where boiling or vaporization is occurring. If we're reducing the amount of heat energy, that's where condensation is occurring. So we see at the regions where we have an incline of the temperature as heat energy is being added, when we want to solve for the amount of heat over those temperature ranges, we will use this equation. Q equals M, which is your mass, C, which is specific heat, times delta T. When we have the solid turning into a liquid or a liquid turning into a solid, or we have our liquid turning into a gas or a gas turning into a liquid, for those points, our temperature is not changing. To calculate the heat, we will use the mass times the delta H of vaporization or the delta H of fusion, depending on which process is occurring. So sometimes we can see sublimation. And sublimation is a physical change in which a substance changes from a solid state directly to its gas state. So when a substance sublimes, the molecules leave the surface of the solid. And at the surface, and as they're leaving the solid surface, they are now held less tightly. So the surface, at the surface of the solid state, these molecules were held less tightly than the interior molecules, and they're able to leave easier and become into a gas state. A good example of when we see sublimation occur is with dry ice. Dry ice is solid carbon dioxide. It doesn't melt under atmospheric pressure at any temperature. Rather, it sublimes. So at below negative 78 degrees Celsius, carbon dioxide or dry ice is in the solid state. Once we reach negative 78 degrees Celsius, the carbon dioxide molecules now have enough energy to leave the surface of the dry ice and become gas state. Let's do an example problem together. We want to see how much heat is emitted when we have 4.25 grams of water condensing at 25 degrees Celsius. Let's pause the video and try this on your own. All right, let's work this out together. In order to complete this problem, we'll need to refer to table 12.2. And that'll give us the heat of vaporization at, here it specifies at 25 degrees Celsius. Of water, which we can find to be equal to 44.0 kilojoules per mole. So now we're told that we have 4.25 grams of H2O. And at the end, we want to find out how many joules or kilojoules of heat is emitted. So looking at this heat of vaporization, the units for that is kilojoules per mole. That means that we need to convert the grams into moles first. So using the molar mass of water, we have 18.02 grams of H2O for every 1 mole of H2O. So our grams have canceled out. Now we can multiply by the heat of vaporization, and we see for every 1 mole of water, we have 44.0 kilojoules. So now our moles of water cancel out, and we end up with just kilojoules of heat. And our answer is 10.4 kilojoules of heat. Let's try another problem that's very similar to this. Here we want to calculate how much energy is released when we have 34.2 grams of water freezing. Pause the video as you try this for yourself. Right, now let's try this together. So for this process, we'll need to find out what the heat of fusion is of water at its freezing point. So we'll refer to table 12.3, and that'll give us the heat of fusion of water, and this is at its freezing point, so that'll have to be at 0 degrees Celsius. Notice in this table, it refers to the melting point, but the melting point is the same temperature as the freezing point. The melting just means that we're going from a solid to a liquid phase, whereas freezing means that we're going from a liquid to a solid phase. But the temperature at which these conversions happen are going to be at the same temperature. So we see that a heat of fusion of water at 0 degrees Celsius is 6.02 kilojoules per mole. Now we'll solve this problem very similar to how we solved the previous problem. So we'll start off with 34.2 grams of water. We'll need to convert that into moles of water before we can use the heat of fusion. We see that we have 18.02 grams of water for every 1 mole of water. So now our grams of water have canceled out, and we have moles of water. Now we can use the heat of fusion to cancel out our moles of water and convert into kilojoules of heat. And we end up with 11.4 kilojoules. This next problem is a little bit more involved. Here we want to look at how much energy is required to heat 10 grams of water from 10 degrees Celsius to 110 degrees Celsius. For this problem, we want to calculate how much energy is required to heat 10.0 grams of water from 10 degrees Celsius to 110 degrees Celsius. So the first thing I'm going to do is I'm going to draw the diagram of temperature versus heat energy to understand the problem that we're encountering here. So the y-axis is our temperature, and the x-axis is the amount of heat energy. So we're starting off at 10 degrees Celsius. And at 10 degrees Celsius, remember, anything between 0 degrees Celsius and 100 degrees Celsius, we are at the liquid state. So we're starting off at just the liquid state. Then we reach 0 degrees Celsius. And at this point, the temperature stays consistent as we're adding more and more heat energy. During this time, our liquid state is converting into a gas state. And then finally, once we've reached just gas state, as we're adding more and more heat energy, the temperature is now rising of that gas state. I'm sorry, this is not 0 degrees, this is 100 degrees Celsius, where our liquid state changes into gas state. And beyond 100 degrees Celsius, we are just in our gas state of water. And we will stop our calculation once we reach 110 degrees Celsius. So we will actually have to break this into 3 different problems. First, we'll need to calculate our 10 degrees Celsius to 100 degrees Celsius. This will be just at the liquid state. And then once we're at 100 degrees Celsius, we have the phase change from liquid to the gas state. And then lastly, between 100 degrees Celsius and 110 degrees Celsius, we are converting into our gas state. Now it's important to note that we're going from 10 degrees Celsius to 110 degrees Celsius and not the other way around. So we'll do a few different calculations here. First, we'll start off at the point that we're between, starting off at 10 degrees Celsius and going toward 100 degrees Celsius. At this point, we need to use the equation that the heat is equal to the mass times the specific heat times the change in temperature. The mass is given to us, which is 10.0 grams. The specific heat of water, which you will have to look up from your textbook, but for water, the liquid state is 4.184 joules per grams degrees Celsius times the temperature change. Now we're starting off at an initial value of 10 degrees Celsius, and the liquid state itself is finishing once we reach 100 degrees Celsius. So our final temperature is 100 degrees Celsius minus our initial temperature, which is 10 degrees Celsius. And that gives us the heat at this point to be 3.77 times 10 to the third joules. Now let's do our second calculation. That's where we're going from our liquid state to our gas state at 100 degrees Celsius. So at 100 degrees Celsius, we do not have a change in temperature. So we need to use the equation Q equals mass times the heat of vaporization here. The mass, again, is 10.0 grams. The heat of vaporization is 40.7 kilojoules per mole. Which gives us well, actually, we're not done with the problem yet. If you notice here, none of the units are actually canceling out. We need to be able to cancel out our grams and our mole. So what we need to use here is an additional factor where we cancel out our moles and convert into grams, or cancel out our grams as well. Our grams has to be in the denominator here to cancel out this amount of grams, and our moles here has to be in the numerator. So for every 1 mole, and this is of water, we have 18.02 grams of water. So now our grams of water will cancel out, and our moles of water will also cancel out. And we are left with 22.5 or 0.6 kilojoules. Notice that our units need to match. So in our first calculation, we ended up with units of joules. So for that reason, let's go ahead and convert our kilojoules here into joules. And that gives us 2.26 times 10 to the 4th joules. And then lastly, we're going from 100 degrees Celsius to our 110 degrees Celsius. So during this temperature shift, we will again use the equation Q equals mc delta T. Our mass, again, is 10.0 grams of water. Our specific heat for the gas phase is 1.996 joules per gram degree Celsius. And our temperature change is our final temperature, which will be the 110 degrees Celsius, minus the initial temperature during this part of our graph, which is 100 degrees Celsius. And when we multiply all that out, we get 1.996 times 10 to the 2nd joules. Now at the end of the problem, we want to see how much energy total was required to heat the 10 grams of water from 10 degrees Celsius to 110 degrees Celsius. So at this point, we need to add up all of these amounts of energy. And our final answer is that our energy total that was required to heat up the 10 grams of water from 10 degrees Celsius to 110 degrees Celsius is 2.2 or 2.66 times 10 to the 4th joules. Or in kilojoules, that would be 26.6 kilojoules of energy.